Hey, how are you doing, guys? This is an exciting day. We are starting officially the second half of calculus. So we know that calculus involves limits and derivatives and integrals, and today we start integrals. So what we're going to do is review a little bit about derivatives, and I want you to look and see that if I ask you to take the derivative of f of x, then I'm going to say f prime of x is equal to 12x. Well, if I ask you to take the derivative of n of x, n prime is 12x as well. And s of x gives a derivative of s prime equals 12x. Was that an accident? Well, no, it's not. So take a look at h, m, and v of x. Can you find the derivative of each one of those? Take a second. Okay, did you get that h prime of x is equal to 12x squared minus 3? And did you get the same thing for m prime and v prime? That's what I'm hoping you got. So 12x squared minus 3, 12x squared minus 3. So is it an accident that I'm getting the same answer 3 times? Well, no, it's not. And if you were in class, we would be doing a slightly different activity. Well, I know that you're good with the derivative power rule at the top part of the chart. What about, do you remember your derivatives of your trig functions? So it's been a little while. Let's make sure we can do these. So is the derivative of g prime going to match the derivative of q prime? And will that match the derivative of u prime? We'll take a look at all three. Do they all three have the same derivative? Yes, they do. And what is that derivative? You're right. It's cosine x. So you're doing a spectacular job. I can hear you all the way over here. So take a look at K, P, and R. It's the same result, guys. So what must be true of multiple items, multiple functions like K, P, and R, in order for them to give you the exact same derivative? Well, do you see that the only thing that's changing is the constant term that follows the part of the equation that actually contains an x. So that's what causes the derivatives for multiple functions to turn out to the same answer in general. Hey, what is the derivative of cotangent x? So the derivative, because it's co, is going to be negative. So it's negative 2. And then what's the derivative of cotangent? Right, cosecant squared x. That's one that you don't see as often, so maybe that was a little hazier in your memory. So what are we building up to? Well, the opposite of taking a derivative is taking an antiderivative, and that's what we're working on. But what is an antiderivative? Well, I say that capital F of x is an antiderivative of little f of x if I take the derivative of big F of x and get back to little f of x. So if we think about taking the antiderivative of little a of x equals 12x, I know I need some function which I'm going to call big A of x to be the antiderivative. Okay, so I know that I need to take the derivative of big A and get back to little a. So if I take the derivative of big A, I'm going to drop an exponent. Oh, okay, so I know that big A of x has to have an x squared in it. So that's where I'm at here. Okay, now think about it. If I take the derivative of big A, I'm going to get a prime of x. And I know that what happens is the power rule tells me to drop the 2 in front times c of x, and then drop the exponent of x from x squared to x to the first. Okay, so now remember, I need the answer for 2 times c of x to equal little a of x, which is 12x. That's what I need to have happen. So that means this 2c of x needs to equal the 12x. So do you realize that that means c has got to be 6? Okay, so what do I know? Oh, okay. That means up here I now know that cx squared would be 6x squared. So again, I'm saying that if big A of x is 6x squared, then that gives me that big A prime, which is supposed to equal little a, does in fact equal 12x. Okay? So it's this game of kind of thinking, what do I need so that when I take the derivative, I get what what I start with? And that's what we're working on. All right, so let's do a little summarizing. So I'm going to say that a of x is an antiderivative, not the antiderivative. Now, why do I talk like that? Because in the chart on the first page, I had f of x, n of x, and s of x, and now I have a of x, and I figured out that a of x was 6x squared. And if I take the derivative of f prime and n prime and s prime and capital A prime, the derivative of all of these gives me little a of x. So f prime of x equals n prime of x equals s prime of x equals a prime capital of x. All of those are 12x. Okay? So all of those derivatives are little a of x. So little a of x has multiple antiderivatives. All right? And so that's why I have to say that one of them is just an antiderivative, not the antiderivative. So it seems like antiderivatives can be multiple answers. That's true. Antiderivatives are always going to be a whole family of equations. So what's that graphical relationship? Well, if you start to graph each antiderivative, let me graph a of x first. Well, 6x squared is just a tall, skinny parabola whose vertex is on the origin. Well, then if I look at f of x and s of x, those are the same parabola, except in one of them I might have the vertex at 2, and in the next one I have the vertex at 3. But otherwise I'm getting the exact same parabola, and it looks like I'm making them taller and skinnier as I go. I'm sorry. I mean for them to all be the exact same parabola. And then n of x obviously is 1, 2, 3, 4, 5, 6, 7, 8. So it's the exact same parabola, but it's got its vertex lower on the y-axis. So the relationship between all the antiderivatives for any given function is going to be that they're all the exact same graph. The only difference is a vertical translation on the y-axis. So each of them is the exact same graph moved up or down from each of the others. Okay? So the only thing that's causing the difference in the graph is the constant term. And the constant term, remember, tells you to move the graph up or move the graph down. Okay? So to avoid saying for every function I want you to find 5 different antiderivatives, we're going to generalize the answer for the antiderivatives by adding a C term on the end. So a lot of people, when I give them a quiz, I'll see them write plus C right at the beginning of their quiz to remind themselves, do not forget to add the plus C when you're doing antiderivatives. So in each of these problems, I want you to find an antiderivative. So on number 1, I need to find capital F of x. Now, I know when I take the derivative of f of x, I need little f of x, which means capital F of x needs to start with an x to the 6th term. So I need to say, okay, If I were to take the derivative, I would drop the 6 down and I would multiply it by what's already there to get 12. So it would have to be 6 times 2 gives me the 12. And then I'm going to add c. Okay? Now, before I go forward, let's double check. So if I do f prime of x, then I'm going to say, okay, 2x to the 6th derivative is 6 times 2 is 12x to the 5th, and the derivative of c is 0. Well, that sure enough does equal the given f of x. That means I did this problem correctly. Okay? I'm going to get a little more focused as we go with this. So on number 2, I need capital G of x. So I'm going to do the same thing. I'm going to say, well, I know that g of x has to be x to the 7th, so that when I take its derivative, it drops to x to the 6th. And I need to say, okay, when I do the derivative, the 7's going to drop down. 7 times what would give me 4? 7 times, 4/7 would give me 4. Don't forget your plus c. Now, let's check that out. And I'm not going to show the check work on everyone, but I do want you to remember this is the way you check your work. So if I do g prime, it's 7 times 4/7 x to the 6th plus the derivative of c is 0. Sorry, the computer, you know how my board sometimes doesn't mark it where I want it to. Well, that is going to be 4x to the 6th. That does equal the little g of x I gave you to begin with. That means I've done the problem correctly. So I'm kind of playing around as if there's not an official method for how you do this. Let me get a little more focused now. Okay? Now, on the next problem, little h of x is not written in a good antiderivative ready format. You should be used to me talking about derivative ready formats. Well, now I'm going to do the same thing, but I'm going to talk about antiderivative ready formats. So in general, what I want is some number a times x to some other numerical exponent b. If I've got it in that format, then doing the antiderivative is super duper easy. So just FYI, that's always what we're looking at doing before we start doing our antiderivatives, okay? So let's do capital H of x now. So here's the deal. I know that I need to add 1 to the exponent. So if I add 1, I'm going to say, well, 2/3 plus 1 is 2/3 plus 3/3. Okay, that's 5/3. And instead of just fooling around trying to figure out what to multiply by, here's the deal. When you took the derivative, you dropped the exponent and multiplied. Well, now I'm going to increase the exponent and divide. So I'm going to say 1 divided by 5/3. And then I've got plus c. Well, I really do not like the way that looks. So I'm going to say h of x is 1 over 5/3, which is 3/5, because 1 over anything means reciprocal of x to the 5/3 plus c. And check it out. If you did capital H prime, do you see that 5/3 times 3/5 does go back to 1 x to the 2/3? So we've got a little bit better method going. Now before I do capital K of x, let me rewrite little k in a more user-friendly format, so a more antiderivative ready format. FYI, if it's derivative ready, it's also antiderivative ready. So whatever you did to get something more ready to take derivatives, you do the exact same thing to get it ready to take antiderivatives. So big K of x equals, so I'm going to say x to the -1, because if I say -2 plus 1, it goes up to -1. Instead of multiplying by, I'm going to divide by the new exponent, and I'm going to say plus c. Okay? So I don't like the way that's written, so let me write it in a better final form. So 3 divided by -1 is -3. X to the -1 drops to over x, and then plus c. All right? So let's do number 5. Now on this one, the only thing that you've got going on is you've got a few more terms. So you still just take the antiderivative term by term by term. So big P of x. All right, so I know x has got to be to the 4th power. So then I take my 8 that's there and divide by 4. I know that x has got to be lifted from x to the 1st to x to the 2nd. So I take the 3 that's there and divide by 2. Now, FYI, 7 is the same thing as 7x to the 0. So if I wanted to break it down that way, I would say lift x to the 0 up to x to the 1st, and then take that 7 and divide by 1. And then don't forget to add c. Most people aren't going to probably go into quite as much detail as I just did. I'm simply cleaning up the first and third terms. And of course, 7 over 1x to the 1st is just 7x. So most people are going to realize if you've got just a 7x, that's what gives you a derivative of 7. They're not going to go into all the detail I did there. And I've got my answer. All right, so far, so good, huh? Now, I'm going to jump right into w of x like I do all of them. I'm going to say, yeah, I've got the idea. Little w of x needs to be rewritten as x to the negative 1. However, when I do big W of x, I'm going to say, well, if I go from an exponent of negative 1 upward, I'm going to add 0. I'm sorry, you can hear my phone ringing in the background. But that would cause me to do 1 over 0 plus c. Sorry about that. So I know I can't divide by 0, so what? What's happening? Okay, so this is not working this way, guys. So what I want you to do is I want you to think differently. I want you to think from the first semester, what did we take the derivative of that gave us 1 over x? So this problem is not a power rule problem. There's something different going on. Have any idea? Great job. Do you remember that if w of x equals ln of x, that w prime is 1 over x? Yeah, and so then don't forget to add your plus c. So sometimes you'll be marching along doing all your exponents, and all of a sudden you'll be like, whoa, and you'll realize that there's a problem there. Okay. So at this point, we're going to look at a couple of simple problems, but we're getting into something called differential equations. This is a major topic, and we'll talk lots more about differential equations in the next chapter, but I'm going to keep throwing little ones out at you now so you kind of get used to it, and the next chapter will kind of be easier that way. But when I look, a differential equation means an equation when I give you a derivative and ask you to find the normal equation. So on number 1, I'm giving you f prime and I'm asking you to find f. All right? Well, I need you to know that taking the derivative of f of x gives you f prime of x. That means f of x is an antiderivative of f prime. Oh, so what I need to do is take antiderivatives of both sides of the initial equation, f prime of x equals 2x. So the antiderivative of f prime is f. The antiderivative of 2x is x squared. I bet you can almost just do that automatically now. Sorry, the screen is writing a little funny. And then don't forget, you're going to have to add plus c. Now, the fact that I'm adding plus c instead of a specific number means I'm getting the general solution. We'll talk about particular solutions on the next slide. Now, when I look at my second problem, I'm asking you to solve the differential equation y prime equals square root of x. Why is it a differential equation? Because I'm giving you a derivative equation, okay? And I'm asking you to solve for the normal equation that has no derivatives. Now, I know from the previous slide that it would be easier for me to do antiderivatives if I write y prime as x to the 1/2. Now, what is the antiderivative of y prime? Y. what is the antiderivative of x to the 1/2? So I'm going to say x 1/2 plus 1 is 3/2. So I need to divide by 3/2 and add c. Okay, so it would be better for me to write it y equals 1 over 3/2 is better written as 2/3, x to the 3/2 plus c. Okay, so that is my general solution. Now let me show you an example of solving a differential equation and getting a particular solution, which is really, this is not bad at all. So I'm going to continue the process I've set up. If I want to solve f prime of x equals 6x squared plus x minus 5, that means I need f of x. Well, what is the antiderivative of f prime? It is f of x. What is the antiderivative of the right-hand side? Well, I'm going to say x cubed is what I need. I need to divide by 3. Oh, 6 divided by 3 is 2, so I'm going to start thinking some shortcuts when I can. So I know that x squared is what I need here. I need to divide by 2, so that'd be 1/2. Let me write that where I mean to write it. And then the antiderivative of, or the derivative of 5x is what would give me -5. So I know that the antiderivative of 5 is 5x, and then plus c. So right now I've got the general solution because I've got plus c and not plus a particular number. But guys, what I'm going to do is say, well, if you have some sort of an initial condition, that means they're giving you a point on the graph of the function that you're seeking. So I now know that 0, 2 is on f of x. So I'm going to plug in the point 0, 2, which means if I plug 0 in for all my x's, then I can plug 2 in for my y. So my y would be f of 0. So I'm plugging 2 in on the y side of the problem. And do you see that means 2 equals 0 plus 0 minus 0 plus c? 2 equals c. That's the easier thing, isn't it? So now what I can do is say, oh, so f of x equals 2x cubed plus 1/2 x squared minus 5x plus 2. Now I've got the particular solution, which just means that you don't have c anymore. You always make sure that you find a number value for c, and then you're done. So your solution's a little more specific. Cool, huh? So we are going to stop right now, and then I'm going to start a new video.